Hi, I'm Christine.
Hi, I'm Jonathan,
Hi, this is Justin.
Hi, I'm Princeton.
and this is our presentation on reactive programming. I'll start by giving a little introduction to reactive programming here, give an understanding of how this style of programming structure works and where it fits with the current development and current market. So, really, reactive programming is restructuring your code to deal with asynchronous data streams. And so first off, we have to define what a data stream is. It is important to note that data streams are sometimes called observables, especially in the Reactive X framework, which we'll get to later. But data streams are essentially objects that emit data over time, often in the form of events. Down here on the left, we have a graphic of a stream which comes for represents Reactive X specifically. We have a stream of data which is on an observable object. An observable object could be anything. It could be a button, it could be a calculation operation, and it will emit value at different points in time. And every time it does, in Reactive X, there are three kinds of methods that can be called: next, error, and complete. Essentially, all of them are responding with events that occur on this data stream. And so while these data streams run along, they return values to be used in the main thread and in other operations. So first off, we need to address why is it called reactive programming, and what would passive programming look like? So passive programming is essentially what most of us are familiar with in the general sense. You've got remote setters and updates. So you have, like on the code section over here where it says cart, add product, product arg, invoice.update, invoice with the product. These are familiar conventions that you're going to see in most object-oriented work. So you're probably familiar with passive programming, and it's probably what you already do. Now, if we take a look at passive programming, if you want to understand the functionality of a system, you have to look at where and how it is used in the program. You would need to search through all of the other files and see, say, if you wrote cart or invoice, right? You need to, if you want to find out how invoice is used, you need to look for where it's used elsewhere, and you find it's found in cart. But as far as dependencies go, a cart knows every other object that it needs to interact with. A cart has an invoice that it updates, its own invoice. We have aggregation and composition. This is really, really familiar. Reactive programming, on the other hand, is dependent on events, observations, and self-updates. So these are the streams that we were talking about before. These streams create just points in their time of data. And if we want to know how a object works in reactive programming, we have to look just inside the actual object itself. It will know already what events it deals with and how it works. We don't need to go elsewhere. However, it's just like it's pretty much the opposite of passive programming, which is obviously intuitive given that reactive versus passive. If you want to identify its dependencies, that's when you have to go and you have to look elsewhere in the program, because the reactive programming style is often built on this similar observer subscription pattern that we're pretty familiar with. If I'm a observable, right? If I'm something that some other part of my program would want to know about, it just comes in and subscribes to me. I don't know about it necessarily, so that is why we have to look elsewhere in the function to know what is subscribing to these data streams. It's a little bit of a different approach, but essentially, like we have here, this code snippet, cart item added event at some given time. Data streams often have time, they are entirely centered around time and asynchronous events. So at some given time, this item was added, and that's added onto the stream. And so if we give that stream over to the invoice is a subscriber, and it watches and it sees that event occurred, it can then use that event, get the data from that event, and create its own calculation on what the cost is supposed to be. So with that being the case, we have the central structure of reactive programming. So reactive programming is pretty commonly used in React Native and Flutter, which are both multi-platform frameworks that are used to build often mobile apps and other kinds of responsive applications that work natively. Both of these are built to work natively and across different platforms. Reactive X is a library used by JavaScript, or created in JavaScript rather, to handle data streams and allow a user to, or a developer to create their own data streams and observables, set up this pattern of implementation in their own technologies just by using ReactiveX. And going forward, we'll have a section for part 1 of the presentation from here on will be the strengths and weaknesses of reactive programming. Part 2 is going to be how we use it, and part 3 will be code samples.
In this section, I'll be covering the strengths and weaknesses of reactive programming. So the strength of reactive programming would be it being a lot more cleaner, concise. It's easier to read as well as scale. It's also better at error handling, and some operators that help to recover from error notifications from an observable include catch, which will recover from an on-error notification by continuing the sequence without error, as well as retry, which will resubscribe to a source observable if it sends an on-error notification in hopes that it will complete without error. You can also avoid callback hell, as well as it being simple to do async and threaded work due to the way it allows you to work on the data streams, which makes complex threading a lot easier. The asynchronous nature of it means that whatever you program it with will offer a smoother, more responsive product for your users to interact with. A lot of operators that simplify the work include delay, which will shift emissions from an observable forward in time by a particular amount, as well as time interval, which will convert an observable that emits items into one that emits indications of the amount of time elapsed between those emissions. Another strength is that it's very simple to compose streams of data, as well as being easy to implement back pressure, and it's responsive, resilient, elastic, and message driven. So this next page will show you kind of a visual of that. So the value being maintainable, responsive, extensible, the form being elastic, resilient, and the means being message driven. This page will cover the weaknesses. So weakness is that it's memory intensive to store streams of data most of the time. There's also a steep learning curve because it needs everything to be a stream, as well as most complexities have to be dealt with at the time of declaration of new services. There's a lack of good and simple resources online to kind of learn reactive programming, and usually when people do kind of look up these sources, they might not be clear between reactive programming and functional reactive programming, which is a little bit different. So there might be confusion on that, and it's not too clear.
In this section, I'll be covering how to use reactive programming. The first thing to consider before you can use reactive programming is you need to consider when to use reactive programming. Reactive programming is an improved alternative to the observer pattern that's designed to deal with events as a stream of values over time rather than a series of unique responses to discrete changes in state. This helps to deal with complex logic behind the event handling code with no loss of expressiveness. It is useful anywhere the observer pattern is common, including user interfaces, video games, networking, and industrial applications. Next, I'll talk about how to use RxJava, which is the Java implementation of ReactiveX, a library for composing asynchronous and event-based programs by using observable sequences. RxJava is made up of 3 key components: observables, observers, and schedulers. Observables are nothing but the data streams. Observables pack the data that can be passed around from one thread to another thread. They basically emit the data periodically or only once in their life cycle based on their configurations. You can think of observables as suppliers. They process and supply the data to other components. Observers consume the data stream emitted by the observables. Observers subscribe to the observable using subscribe on method calls to receive the data emitted by the observables. Whenever the observables emit the data, all the registered observers receive the data in the onNext callback. Here they can perform various operations like parsing the JSON response or updating the UI. If there is an error thrown from the observable, the observer will receive it on an onError method call. RxJava is for asynchronous programming, and we need thread management. This is where schedulers come into the picture. Schedulers are the component in RxJava that tells observables and observers on which thread they should run. You can use observeOn method call to tell observers on which thread you should observe, and you can also use scheduleOn to tell the observable on which thread you should run. Here is an example of a code snippet where you can see the three key components of RxJava mentioned before. The first key component is creating an observable that emits data. Here, the database variable is observable, which emits the data. Just is just an operator which basically emits the data provided in the argument one by one, which is a string in this case. The second key component is creating an observer that consumes the data. In this code snippet, the observer consumes the data emitted by the database observable. It processes the data received and also handles any errors inside it. The third key component is managing concurrency with the scheduler. SubscribeOn method call tells the database observable to run on the background thread. ObserveOn method call tells the observer to run on the main thread. This is the basic code example of how reactive programming is used with RxJava.
On this part of the presentation, I will be talking through some code samples that will help give a good explanation for how reactive programming can be very beneficial. This here is a simple counter application written in Flutter or Dart that uses the block pattern, or business logic component pattern, which was created by Google and uses reactive programming to handle the flow of data. Some benefits in using this pattern we will review are separations of responsibilities, testability, freedom to organize layout, and reduce the number of builds. The first benefit mentioned was separation of responsibilities. This code snippet shows how you can remove the business logic from the counter page class, so it only needs to worry about displaying the counter, which is only refreshed when necessary, and provides a button which, when hit, requests an action to be performed on the counter. This is a great example of how reactive programming, separating the business logic from the front, is very, very beneficial. Next was testability. Testability makes testing business logic much easier. Having this class called increment block to be able to test the business logic without having to use the user interface is extremely beneficial to any back-end developers. It's also quicker and much easier to use for most back-end. The next was the freedom to organize the layout. Using streams, you can organize layouts independently of the business logic. Any action could be launched from any place in the application by calling the increment countersync, and you may display the counter anywhere in the application by using the out counter stream. Having the ability and freedom to be able to do this anywhere within the application is a huge plus, especially when developing. Next was reduce the number of builds. Using Stream Builder instead of set state, this drastically reduces the amount of builds to only the ones which are completely required. This is a huge improvement from a performance perspective.
Here's a quick example or run through of what this application actually does. As I press the counter, this button, this floating button, only is responsible for displaying the button. It is not responsible for the counting. Again, the counter is only responsible for displaying the counter. The logic or business logic is not involved in these components. the back-end business logic is only dealt within the back-end. This is the best way to program for mobile development and many other programming or programs.
Thank you.